Hello everyone, my name is Maurizio Azzan and I'm from the Conservatory of Mantua in Italy. Together with Luca Guidarini, also from the Conservatory of Mantua, and Ingrid Pustianaz and Michele Leggeri from the University of Pavia, we are part of the Corp research group. Corp brings together composers and musicologists to investigate and systematize recent practices in contemporary composition and orchestration related to the use of so-called complex sounds. In this presentation, Luca Guidarini and I will present our work on the preparation of string instruments. We propose a theoretical model and an operational taxonomy aimed at understanding how commonly used preparation techniques act on strings and influence their spectromorphology. Building on this framework, we discuss the specific case of string preparation using Padafix and Clodespins, and introduce a dedicated sound database designed from integration into the computer-aided orchestration software Orchidea. I will begin by introducing the theoretical model and taxonomy, and Luca will then present the case study and the sound database. Among the new orchestration practices that have emerged in experimental contemporary music over the last few decades, the preparation of string instruments has become increasingly important. Patafix, paperclips, hairpins, clothespins, and aluminium foil are just a few examples of the materials that have dramatically expanded the timbral palette of string instruments. These and many other materials have enabled composers to explore a wide range of complex sounds, often leading them to make highly specific material choices even when several alternatives could produce very similar sonic results. Despite the growing use of these techniques, however, we still lack an operational organological model that can adequately describe them and support more informed orchestration strategies, especially in the context of computer-aided orchestration. To develop such a model, we need to shift our attention from the final acoustic result to the conditions that produce it. In particular, we need to address a few fundamental questions. How does a preparation act on the sounding body to which it is applied? How does it modify the sound production process? And what relationships emerge between the material and position of the preparation and the resulting sound? According to Mark Raybrook, a musical instrument and the performance body can be understood as an adaptive system. In Raybrook's words, this adaptive system is characterized by its ability to construct meaning out of the perceptual sounding flux through adaptations at each level of its functioning within a continuous feedback process. Introducing an external element into this system inevitably alters its functioning and leads to a reconfiguration of its internal relationships. But what happens when the external element is a preparation applied to one or more parts of the instrument? In 1975, Herbert Haidt proposed an organological model in his Grundlagen der natürlichen Systems der Musikinstrumente. In this model, each human instrument pair is conceived as a dynamic system made up of interconnected elements. Each of these elements has a specific function, and together they establish a relation of spectromorphological codetermination. In other words, every element contributes in its own way to shaping both the spectral content of the sound and its temporal evolution. By integrating Haidt's model with subsequent developments in acoustics, we can describe bowed string instruments as systems composed of 5 main components. First, the muscular system, which provides energy and acts as the exciter. Second, the bow, which channels this energy into the string and determines its excitation regime, acting as a mediator. Third, the string, which works as a transducer, transforming the energy delivered by the mediator into mechanical oscillations. Fourth, the bridge, called the channel by Haidt, which transforms the motion of the string into forces applied to the soundboard, thereby modifying the instrument's frequency response. And finally, the body of the instrument, which selectively filters, amplifies, and radiates the string's vibrations, acting as a resonator. It is important to stress that the system described here is not perfectly linear. For this reason, identifying the role of each of its components in spectromorphological codetermination requires us to consider an idealized performance situation, in which a single sound is produced under conditions of constant bow speed, pressure, and position, with an open string and a motionless instrument. In such a situation, the transducer defines the frequency space within which the energy is distributed. The mediator determines how this energy is distributed over time, while the channel and the resonator selectively filter some of its components. Within this framework, a preparation can be understood as a modification of the operating conditions of these elements without changing their organological functions. In practice, the application of external objects to the strings, bow, bridge, or body of the instrument, as well as the partial or total replacement of their constitutive elements, reconfigures parameters such as their geometry, material, mass, mechanical impedance, and conditions of contact and friction, thus modifying their spectromorphological contribution. In this way, preparations turn these properties into controllable parameters within a standardized instrumental model, and in some cases, introduce additional organologically functionalized elements. For example, preparing the bow modifies its stick-slip mechanism, thereby altering both the way energy is transmitted within the frequency space and its temporal articulation. Likewise, applying mutes or additional resonators to the bridge modifies its lever action and frequency response. In turn, placing external objects on the body of the instrument selectively attenuates specific resonance frequencies. As for the strings, preparation reconfigures their organological arrangement by introducing an impedance discontinuity. The preparation acts both as a constraint, partially dissipating and reflecting vibrational energy, and, when it is not in contact with the nut or the bridge, as a channel that transmits part of this energy to the portion of the string not directly excited by the bow. As a result, the frequency space is influenced by parameters such as the preparation's acoustic conductivity, inertia, density, shape, weight, and position, all of which co-determine the mechanical impedance of the system. The closer the impedance of the preparation matches that of the string, the more efficiently energy is transferred. Consequently, the signal radiated by the portion of the string that is not directly excited by the bow may become strong enough to exceed the masking threshold imposed by the bowed portion. Building on the taxonomy we presented last year at the Actor workshop in Geneva, we introduce a new class of complex inharmonic sounds, which we define as multispectral. Our updated taxonomy distinguishes three main categories. The first category is balanced sounds. These result from the coordination of the left hand, the string, and the bow, with the aim of balancing the harmonic components of the spectrum and promoting a clear perception of the fundamental frequency. The second category is filtered or equalized sounds. These are produced by filtering or equalizing the string's harmonic spectrum, and typical examples include the bandpass filtering, low or high shelf attenuation, as in the case of rubber or EV practice mutes, and resonant peak filtering. The third category is complex sounds. These result from an interaction between the left hand, the string, and the bow that produces a spectrum in which energy no longer decreases linearly from low to high frequencies, but is instead redistributed or even amplified in the upper frequency range to compensate for a loss of energy at the fundamental. Within this category, multispectral sounds are characterized by the coexistence of multiple spectra. They are therefore distinct from both noisy complex sounds, such as altast overpressure, and complex harmonic sounds, such as multiphonics. This distinction between noisy and multispectral sounds allows us to relate the organological model to its perceptual outcomes, making explicit the relationship between the topology of the vibrating system and the resulting spectromorphological organization. At this point, I will hand the floor over to Luca, who will present a specific case study and the final results of our analysis.
To analyze the sound categories presented by Maurizio, we are developing several databases, each built around a different string instrument and preparation technique. The corpus presented here extends and refines the work on violin recordings first introduced at Actor Y7 last year. The cello corpus presented here was recorded by cellist Alessandro Mazzacane, who prepared each string with parafix, a small clothespin and a large clothespin. Analysis draw on music information retrieval techniques, using audio descriptors from the library Essentia, here comes PM2, PWin, and SuperVP algorithms, alongside STFT analysis to identify prominent partials and their amplitudes. Essentia, developed by the Music Technology Group in Barcelona, is an open source library with hundreds of algorithms, covering spectral, temporal, and tonal descriptors. We drew mainly on two of its tools, spectral centroid and predominant pitch melodia, a contour-based pitch estimator originally designed for polyphonic melody extraction, but useful here for isolating dominant pitch from noisy and inharmonic spectrum. Spectral spread comes from Here Comes Descriptor library, the standard deviation of the spectrum around the centroid, indicating how concentrated or dispersed the energy is around that central point. Also, PM2 and SuperVP come from Here Comes Analysis and Synthesis team and share the same but updated sinusoidal plus noise modeling core behind the whole audio sculpt. They track individual partials over time, frame by frame, which is what lets us follow how a single partial's amplitude and frequency evolve and tends to emerge with different preparations. Again, for pitch, we use PWin, a probabilistic extension of the original Win algorithm, and instead of committing to one pitch estimate per frame, PWin generates several candidates with associated probabilities and resolves them through a hidden Markov model. STFT analysis complemented all of this, letting us locate the most prominent partials directly in the spectrum and measure their amplitude without going through any pitch model at all. This served as a useful cross-check against the other algorithms, and it's also what we use to transcribe the partial and their amplitudes into musical notation for the visualization. An interface for visualization and navigation gives access to this data along several dimensions, ordered on the x-axis by position on the fingerboard of the instrument. For every sample, information about the kind of preparation, the string, the position, and the related file name is given. Let's look at the dataset through the interface. Three colors encode the preparation type: red for parafix, green for the big clothespin, and magenta for the small one. The pitch estimation is a comparison between 5 different algorithms, each chosen because it approaches the problem from a different angle. These are SuperVP's maximum spectral peak, PM2's detection of inharmonic partials, Melodia's predominant pitch estimate, Super VP dedicated detector for percussive and inharmonic material, and P-Yin's estimate. Alongside these, the interface showed the standard deviation across the 5 pitch estimates. The standard deviation across algorithms serves as a double function. It measures error, but it also acts as a signature of the prepared sound itself. Because a single signal can contain several simultaneously plausible F0 candidates, each algorithm locks onto a different one, and the resulting disagreement among algorithms becomes a quantitative trace of the machine listening ambiguity that characterizes this category of sound. Here the spectral centroid of the entire dataset is ordered by the pitch of the played note. Right away you can see the 3 preparations occupy distinct regions of the timbral space. They don't overlap randomly. It's possible to see how the parafix traces a coherent, narrow, larger linear trajectory in which brightness scales with pitch. The mechanical and consequently spectral behavior of the perturbed strings remains consistent across the different strings, and overall this preparation produces the darkest timbral profile. The two closed spin, clip big and clip small, sit systematically higher and with greater dispersion. Their centroid decouples from the played note, showing that the preparations reconfigures the instrument's overall physical and spectromorphological behavior. Now, the output of the Super VP F0 percussion, the most accurate of the pitch estimation algorithm, is compared across the chromatic scale on the second and fourth string. On both strings, the dispersion of the closed spin data becomes markedly more pronounced from the first octave of the fingerboard onward, a threshold that is geometric in nature. As the stopping point nears the half-length point of the vibrating string, the preparation sits at 1/4 of the open string length from the bridge, maximizing its mass loading effect on that mode. Beyond this threshold, the two strings expose the impedance gradient directly. On the second string, with lower characteristic impedance, the dispersion is broad and chaotic. On the fourth string, with higher impedance, the same preparation yields clusters that run more orderly parallel to the parafix curve. To sum up, we have tried to show that string preparation is a structural reconfiguration of the human instrument system described by Hyde, and treating the preparation as a modification of mechanical impedance lets us connect the sound production to specific measurable spectromorphological outcomes. The cello corpus and the analysis presented here confirm this connection. The three preparations occupy distinct regions of the timbral space, and the geometric threshold we observed around the half-length point of the string shows that impedance has a direct predictable effect on where and how energy distributes itself across the spectrum. This work is still ongoing, currently extending the corpus to other instruments and preparation types. Thank you.